In this tutorial, we are inspecting dials using the Unsupervised Red tool. Before using the Red tool, we need to ensure that every dial is in the same orientation. We do this using the Blue tool, and we add images. Here are our images. You can see that some of them contain the word bad. These are the bad images, and there are others that are just numbered. These are the good images. Then we select the region of interest. We can apply. We have selected the whole image as the view, and we can now label two features. And these two features will allow the software to place every dial in the same orientation. It needs two features because that way we can have both the position and the angle in which the dial should be placed. Because as you see here, every dial has a different orientation on the image. So we label the first feature, for example, the center circle. It could also be another distinguishable feature on the dial, such as any of the other circles on the dial. We notice that the feature size is not large enough for this feature recognition. It is much smaller than the feature we are looking for. So we can increase it to 100. We could even increase it a little more, but 100 seems right. We can pick a second feature, which is smaller than the first, and matches our feature size perfectly. We need to make sure that the second feature is labeled differently from the first. We enter 1 so that the software recognizes that these are two different features. After labeling the first view, we need to create a model. To do this, we right-click, select Create Model. This model will be useful for the tools that we used. In this case, it is the Red Unsupervised Tool, following the Blue tool. We can name this model Dial. Threshold indicates the tolerance given by the software, so 100% is little tolerance, meaning that it will try to match our model exactly. And 0% is very tolerant, so the software will find matches to everything, which we do not want. So 50% is a good choice. The occurrence is set to 1 because there is one model on every view. For each parameter, you can see a description when you hover your mouse over the names. The search space gives several parameters we can adjust. For example, the angle of the models. In our case, -180 to +180 will be fine, because we observe that every view has a dial in a different orientation. 360-degree rotation across these views. So we can check the angle box. The scale refers to the size of the original model, so 100 is 100%. It fits the scale of this model exactly, and 1 would be much closer to the feature 0, so it would be, for example, around here. And here, our scale from 1 to 100 means that the feature 1 can vary from position at number 1 to a position at 0. This is not really what we want, because in our case, it would be better to have a position around 100% of the scale. So for example, it could be 70. That's a bit large. Let's do 80 to 120. The x and y coordinates indicate the position of the model. In our case, it would be easier to move this model on its origin. On the feature 0, move origin to current mode. And here we know that feature 0 is always in the center of the picture. So it means that on this percentage, the 0 percentage should be around 50%. So we enter 35%. It may be a bit large, so change it to 40% and 60%. Enter the same for the y coordinates. Now we have our model, and if we move our two features slightly, the software automatically finds them. We can continue to label our images. Four to 5 images should be enough for the software to train. Since we have 100% trained selection, this should not be a difficult task. Now we have 5 images labeled. Another thing that we can do is look at the perturbation. We can add in the training. In this case, since the dial will move in the image, the rotation should be set from 0 to 360 degrees. And now we can train. After training and processing are complete, let's take a look at the results. We see on the right sidebar that there are 21 models found. This corresponds with the number of views. Hopefully this means that all models have been found correctly. To verify this, we will look through the images. This one should be trained again. The features are showing in the incorrect spots. In this model also, we will need to train again to correct the mistakes found by the software. The rest of the models look good. Now retrain. And now we should have found every model correctly. We can take a quick look through to confirm this. Now that our blue tool is ready, we can add the next tool, the Red Unsupervised Tool. We need to select our region of interest. We can enlarge the ROI, which is a square, to include the entire dial. When we are happy with the size of the ROI, we will click Apply. Now we see that all of the dials have the same orientation. This is thanks to the blue tool that we added. Specifically, the model allowed this uniformity of the orientation. So if we look at the ROI, we can see that the model we selected is the dial model from the blue tool. The next thing to do is to label the good and bad images. So initially, we will label all of the images as good, and then we need to select which images are bad. We know that the bad images have the word bad in their file names. If we simply type bad in the display selection, we will find all of the bad images. Here you can see that there are 9. Actions for 9 views. Label views bad. And now all of our views are labeled. 21 views in total. We need to edit the mask. You will right-click on the view and select Edit Mask, or Control-M also works. One way to do this is to mask the entire dial with the circle tool. And then invert it. Another way to do this is to use the magic wand and select the area surrounding the dial, which we are not interested in. To use the magic wand, you need to hold the click, and the more that you hold, the more tolerant the threshold will be, meaning more of the image will be masked. We can finish using the line tool if this is not perfect. But in the end, it looks like the disk mask would have been the more efficient approach to take. Click Apply. Apply this mask also to the tool and all views. Yes. We need to be careful because there are holes in the dial that we do not want the software to analyze. We will use Edit Mask and the Disk tool to fill in all of the holes we do not want to be found. In total, there are 6 holes that we do not want the software to find. And finally, for this piece, we can use the magic wand. The more you hold it, the wider the mask will be. Apply to all views. Now we have the same mask for all of the views. This is why it was important that all of the dials were in the same position with the same orientation. One final thing to make note of before training is that we have very few images for training. So if we look at the good images, which are used for training in the unsupervised Red tool, there are only 12 of them. If we have train selection as 50%, this means that we are training on 6 images. It is very likely that this will result in an overfitting from the software, leading to bad results. Because there are so few images, we can set the train selection to 70%, which will be a bit better and should give us better results than at 50%. We are now ready to train. After the training and processing, the results are not perfect. There are some misclassifications. We can take a look at which images are misclassified. We can see here that there is a reaction at this point, and if we look at the raw image, we can see that this could be a real defect that the software has detected, although this image has been labeled as a good image. A significant improvement can be reached using a different capacity and also adjusting the training passes. Simply hover your mouse over the name to see a description of these 2 parameters. The capacity describes the complexity that the software can deal with. It should be adapted to the situation, the images that we are dealing with. For simple images, it can be set to small or medium or even tiny. But in our case, the defects are difficult for the software to see. Therefore, there should be a higher capacity. This means that the training will be done using more resources, and this will be tuned to analyze images better. If the capacity was too low, it would lead to what is called underfitting, meaning there are not enough resources, not enough parameters from the software for the analysis. Similarly, for an easy analysis of another set of images where the defect would be easy to recognize, capacity should be set low, because otherwise it will lead to an overfitting, meaning there are too many resources, which leads to bad performance, since we do not need a lot of parameters set. In our case, we selected the huge capacity. The training passes will be modified to 2 training passes. This means that there will be several trainings from the software. The first training will be the way it was originally done, but the second will focus on the images that have a score that is very different from the score it should have. This is what increasing the number of training passes does. It focuses more on the difficult images. We can now train. We observed that the change in capacity and training passes leads to a significant improvement in the performance. All of the images are correctly classified. And if we lower the threshold, it is interesting to note that if we look at the good images, we see that the software reacts on what could actually be defects. So it can help detect defects that were not seen by human inspectors.